Intro music. Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Romy Rodri guez Marti nez with us today. Hey, Romy.
Hi.
How are you?
Thank you for having me.
Oh, well,
I'm good.
Thank you for coming on. It's really great. Let's see. What is your geolocation? And we got a freeze.
Puerto Rico.
There we go. We're back.
Oh no.
It's real life.
Yay.
Things happen. So what's your
Yep.
geolocation? Where are you at?
So I'm in Puerto Rico right now visiting my parents, but I do live in Columbus, Ohio, where
Okay.
I go. Yeah.
Okay. Are you there on in Puerto Rico as a vacation or summer? Have you been there through the whole pandemic or?
I've been here for a little while, yeah.
Okay.
Just came and been chilling with my parents because I can.
Oh, this is gonna be good. Okay, come back, Romy.
Can you hear me?
You're breaking
Can
up
you hear
quite
me?
a bit.
Oh no. Yeah, it's just my internet is a little bit unstable. So
That's okay. We'll go. If it gets really bad, then we'll reschedule it or better.
it's not usually like this, but this morning it's been a little bad.
All good. So I'm in Phoenix. It's May 28th. Summer is coming in Phoenix. We'll hit about 35, 36 C today. Probably in another week or so, we'll hit the power switch and go on up to 40. So I imagine that summer has hit in Puerto Rico already.
Oh yeah, for sure. I have a fan right next to me and it's on at all times during the day.
Very cool. Very cool.
Yeah.
So where are you in your trajectory at the Ohio State?
Yes. So I'm a fourth year graduate student.
Cool.
I'll be a fifth year now in the fall, and I'm working with Professor Scott Gowdy.
Very good. Very good.
Yeah.
So you are about to be Dr. Romy.
Hopefully.
You'll do great. It'll be good. So speaking of that, as you head into your fifth year, Romy, what do you like to do for research?
So I've worked on a few different projects at Ohio State, but mostly they're all related to exoplanets, broadly speaking. So the first project that I worked on was looking for flares on M dwarfs, and that is, yeah, so it's important for habitability. We know that M dwarfs have a lot of small, potentially habitable planets, and so that was my first project, and then. But then I worked on the detection of hot Jupiters with Professor Scott Gowdy as a collaboration with the Kelp collaboration. And now I'm working on modeling small, potentially rocky exoplanets and trying to understand more their interior structure and things like that using measurements of their masses and radii.
Very cool. Very cool. And that is going to bring us to this very lovely APJ article on analytical estimates of the achievable precision on the physical properties of transient planets using purely empirical measurements. And Romy, take us away.
Yes, thank you. So yeah, as you just said, in this paper, we are presenting analytical or analytic approximations of the precision that we can achieve on the physical properties of transiting exoplanets. And by properties, I mean, in particular, the radius, the mass, the density, and the surface gravity. And with empirical measurements, we mean that we, in this paper, try to express these properties and their uncertainties in terms of only transit and radial velocity observables. So the orbital period, the transit duration, and things like that. And so the motivation for the paper began with the question of whether we could measure the surface gravity more precisely than the mass. And the reason behind this was we thought that the surface gravity could be even a more important parameter in terms or diagnostic of potential habitability. And so it began with this question of, is surface gravity an important parameter? And if so, how well can we measure it? So that was a bit of motivation. And to give you a bit of background on the field and why precisions are important, up until very recently, it has been difficult to obtain precise masses and radii of small exoplanets in particular. And by small, I mean less than approximately 4 times the size of Earth. And that's because most of these planets were discovered by the Kepler mission. And Kepler was primarily looking at faint stars, which were not very amenable to follow-up observations. And so we didn't have the masses for a lot of these planets. And thankfully that started to change with the Transiting Exoplanet Survey Satellite, or TESS, because TESS has been focusing mostly on the nearest and brightest stars. And these stars are amenable to follow-up observations. And in fact, like one of the main science drivers for TESS was to measure masses of at least 50 planets, right? And so that was one of the missions. And currently we are, I think, more than half of the way there, because as of now, I think more than 30 have been discovered.
Okay.
So we're in good shape. And of course, a lot of candidates are trickling in every day. And in total, I would say there are over 300 planets, small planets, that have masses and radii measured to better than 50%. Okay. And yeah, so 50% is a good number, is a good precision for most planets. But for the smallest planets, which have thin atmospheres, or we think have thin atmospheres, they're very compositionally diverse. And in order to try to understand their composition and place constraints on their internal structure and things like that, we need to achieve very high precisions. And so that's part of why we're doing this. Okay. The other big part of the motivation for the paper is that traditionally, stellar properties like the masses and radii have been derived in a sort of have relied heavily on stellar evolutionary models and stellar evolutionary tracks, right? You've heard about MESA, the MISS models, the YY and the torus relationships. And normally these relationships, these models, make a number of assumptions about the types of stars that are being used. And so, for example, they will assume that the stars have solar Fe upon H, solar metallicity. Yep. And if the stars that you're working with don't satisfy those assumptions, then that will lead to incorrect inferences about the stars, which will propagate to incorrect inferences about the planets. And so it is necessary and important to have to be able to derive things in an empirical way. Yes. So yeah, so that's basically the background for the paper. And now we can begin with equation 1. So the goal was to derive all these properties in terms of transit and radial velocity observables. So we started with the surface gravity, expressed here in equation 1 in terms of the planet mass and radius. So what we did is we rewrote this equation in terms of K, the radial velocity semi-amplitude, and which is that equation 2. And for all these calculations, I should note that we are assuming a circular case, assuming a simple case of a circular orbit, an equatorial transit, and no limb darkening. So these are very simple expressions. But basically, after a little bit of algebra and rearranging, we end up with, yeah, that expression. And we can go scroll down a little bit, down to the next page. There's just a lot of substitutions that just might be not very exciting to go through. But the bottom line is, after all these substitutions, we end up with equation 11.
Yep.
That's the important, right? Yep. And as you can see, we began with MP over RP squared, but now you see that it can be rewritten only in terms of radial velocity and transit observables, which are K, the radial velocity, semi-amplitude P, the orbital period, the transit depth delta, the transit duration T, and tau. And all those things are direct observables. So they're purely empirical quantities. Okay. And if we use linear propagation of error, we can get an estimate of the fractional uncertainty on the surface gravity, which is, yes, equation 12. Yep. And as you can see, it depends on a combination of all those same parameters. Any questions so far?
Okay, tau is the ingress-egress duration. So
yes.
Got it. Okay.
Yeah, the time it takes for the planet to just enter the stellar disk.
Okay, I'm with you. Good.
Awesome. So then, yeah, we just went ahead and did a similar process for the planet mass, which in this case, we can already use the surface gravity, since the surface gravity included exactly depends on the mass. So you can sort of piggyback from the surface gravity, and you end up with equation 15. And again, using linear propagation of error, we arrive at this expression, equation 17, for the fractional uncertainty on the planetary mass. And if we compare equation 17 with equation 12, you will see that the only difference between them is the extra term of R star. Mm-hmm. And so already you can see that so the surface gravity will be measured more precisely if written in terms of these quantities, just because it depends on one less parameter.
Fair enough.
Awesome. And then, so the planet density, we did a similar thing. And again, we can use the fact that we've already derived the previous expressions, and we end up with equation 19, very similar equation as before. And we end up with equation 20 with the fractional uncertainty that depends on all the aforementioned parameters. And then, finally, we also trivially derived the uncertainty in the planetary radius, which is the next equation on the next page. That one is the most trivial, just because if we assume no limb darkening, then it's only, dependent upon R star and the transit depth. So it's a very simple expression. And if we compare all these fractional uncertainties, we see that there emerges this hierarchy in the precision in which we can measure all these properties. And the hierarchy is that the stellar radius, or the planetary radius, will be the most precise, or the easiest to measure, followed by the surface gravity, then the density, and then the planetary mass. Okay. And that is because, as you saw, the radius is the most, the simplest one. Yep. Only depends on two quantities. Yep. And then the surface gravity doesn't depend explicitly on the stellar radius. And so, and so that means that it will be generally easier to constrain if it's written in these terms. And that's surprising, because I was personally expecting the mass to be the best measured parameter, and it ended up being the worst. And so that's the main result. And I guess we can go to figure 1.
Okay. Let's see. Let's take a look at figure 1. Okay. Make that nice and big, and there we go.
Oh, can you hear me?
Yes, we can.
Okay, I'm back. Sorry, my internet is just not great today. But yeah, so so in figure 1, so what we did is we tried to test these analytic approximations by taking a few examples of previously characterized papers from the literature. So we took 5 systems, 2 hot Jupiters and a few systems that are either super Earths or mini Neptunes. And so what we did is essentially we took the transit and radial velocity observables from the discovery papers, and we plugged in those values into our equations, and then we compared our results, our analytic fractional uncertainties, to the ones reported in the papers.
Right.
And so that's what you're seeing here. On the y-axis are the fractional uncertainties reported in the literature. And in the y-axis, we have the model-independent uncertainties that we derive with our analytic approximations. And then the diagonal line is just a one-to-one line for reference.
Yep.
And the different colors are just represent the different planets. And the symbols correspond to the different planet parameters. So the diamonds are the masses, the squares are the surface gravities, the circles are the densities, and the triangles represent the radius of the planets. Okay. And so you can see here that almost all the planets lie on top, right on top of the one-to-one reference line, which means that there's a very good agreement between our analytic approximations and the ones from the literature, which is good. And it means that our equations are generally reliable, even though they're very simple. They can be used to estimate the uncertainties in these properties. There were a few exceptions, and I'm sure you're wondering what these arrows are.
Yes, you read my mind.
Yes, so I'll get to that now. So there were 2 systems that were pretty discrepant, and those are K2106b in brown and HD 21749 in gold. Yep. And for those systems, what happened is that the authors in these who analyzed these systems used external constraints, such as so they basically placed priors on M star and R star from stellar evolutionary models. Got it. And so for the case of HD 21749b, what happened is the priors that they use from the stellar evolutionary models were actually tighter, or the uncertainties were smaller than the rho star, or the stellar density that you would infer from the data. So from the light curve and the radial velocity. And so in this case, they adopted the tighter constraint on the stellar parameters, and so that propagated to smaller uncertainties on the planetary properties, and so that's why they are all systematically smaller than what we estimate. Okay. And in the case of K2106b, it was a similar thing, but the opposite, in which the authors used the constraint from the data, but the constraint from the data was actually weaker, and they still went ahead and adopted that prior. And so that's why in this case we get a tighter constraint, or smaller fractional uncertainties.
Right.
And so that is why these two systems are sort of a little bit discrepant. In the rest of the cases, the authors didn't really use constraints from stellar models. And so that's why we get a pretty good agreement. And but yeah, that's basically what happened there. And then when we actually go back and try to reproduce what the authors did in the original papers, then we recover their uncertainties. And so that's what the arrows are. They're pointing from our initial estimates to the ones that we recover once we do a more careful analysis of what they did.
Okay, great.
Yes. So that's it for this part of the paper. Do you have any questions?
I'm good so far.
Awesome. So the other main thing that we addressed in the paper was the importance of surface gravity, going back to that parameter. And in particular, we explore the connection between the surface gravity and the core mass fraction of a terrestrial planet. Both of these properties are important for the habitability of a planet. So in different ways. So I'll start with, thanks. That's exactly the question, the equation. Yeah, 54. Yeah. So scroll a little bit down the next page.
Yep.
So yeah, so here's where I talk a little bit about why surface gravity is important. So one of the reasons is it determines the scale height or the thickness of the atmosphere of a planet, along with the equilibrium temperature and the mean molecular weight.
Yep. And
that's important because it has important consequences for, whether the planet will have weather and things like that, which are important for habitability, of course. And then the other main thing is that we think that the surface gravity may also be a driver of plate tectonics. And plate tectonics on Earth, as you know, is very important for habitability. It controls a lot of geological and atmospheric processes. One of the things it does is it takes some of the CO2 from the atmospheres and it transports it to the interior, so that we don't get into this like runaway state, like greenhouse effect, like Venus. And the other thing is it helps drive the formation of, topological features like mountains, and earthquakes, are caused by plate tectonics that are moving below the surface. And so it's a very important parameter. And also the core mass fraction is crucial for things like whether the planet will be able to, during the formation process, if it will be able to accrete an atmosphere and hold on to it. And yeah, which is, the most important thing. And then also it controls the strengths of the magnetic field. And the magnetic field is also super important. It shields us from the solar wind, solar flares, things like that. So also super important factor. And so in this paper, we, I guess we can scroll down to the other figure. Yes. So we explored this, we considered the planet K2-229b, which is one of the most strong candidates for a so-called super Mercury. So super Mercuries are these planets that have been discovered in recent years, which are very dense. They're usually denser than pure rock or than the Earth. And we suspect that they're likely iron enriched. And the reason we call them super Mercuries is because in the solar system, Mercury is the only rocky planet that has a very large core mass fraction of about 70%. The other rocky planets have about 30%. And it's inconsistent with the core mass fraction that we would expect based on the chemical abundance of the sun. right? So, and so that's why we call these planets super Mercuries, because when we place them on these mass radius diagrams, we see that they lie on top of these like Mercury-like, composition lines. And so this planet is one of them. And it has already been studied, but in this paper, we calculated the core mass fraction rho, which is the solid blue line there in the middle of the, so any planet going through that line would have a core mass fraction of about 56%.
Okay.
Which is what we get for this planet. For reference, the core mass fraction of the Earth is 33%. So this is a much larger core. And so that CMF rho is the core mass fraction that we expect based on just the mass and radius of the planet, whereas CMF star below it is of 29% that we estimated is the core mass fraction that we infer, assuming that the planet has the same refractory abundance as the star, which we know that for Mercury is not the case, and it seems that it isn't the case for this planet either. And that's why we calculate both of these quantities, right? Because by comparing CMF rho and CMF star, then we can infer whether this planet is chemically anomalous. Why, if it has a core mass fraction that is inconsistent with the one that we expect from their host star, then that tells us a lot about the interior composition, and it gives us clues about what could have happened to this planet, that it became iron enriched either during formation or after formation. Maybe it was late stage bombardments or impacts and things like that like stripped some of the mantle, and it left the core more exposed and things like that. We don't really know what the causes are, but in any case, so we calculated this for this planet, and so what this figure is showing is the mass and radius uncertainty ellipses for the planet. So the red ellipses that you see here are the uncertainties, the 1 sigma and 2 sigma uncertainties, if we assume that the planet is, that the mass and radius are uncorrelated. And the black ellipses correspond to the uncertainties in if the mass and radius are correlated via the additional constraint of the surface gravity.
Right.
And you can see that if you look at the black and red ellipses, the 1 sigma and 2 sigma ellipses are tracing this line of constant CMF more closely. It's like more stretched around this
direction.
Right. It's like tilted in this direction. And so that means that if we have the constraint of the surface gravity, we can get a better constraint on the core mass fraction. And this is useful for 2 reasons, because the core mass fraction is very uncertain. It's not a directly observable property, of course, and it's uncertain even for the rocky planets in the solar system, just because it's very hard to probe the interior. And the other reason it's useful is because, as we demonstrated in the paper earlier, the surface gravity may be one of the best measured properties. And so that is something useful that we can do with this property if we have a handle on it, and we only need these empirical constraints.
Yep.
So that's basically it. Oh, something I forgot to bring up earlier is one application of the equations. And so one of the applications is if you're thinking of reanalyzing a system that has already been characterized, but let's say you have more data,
right.
Or let's say you now with all these Gaia data releases, let's say you have better parallaxes, and with these better parallaxes, you have an idea of how much better you can constrain, or you can reanalyze the star and get a better constraint on the stellar radius, right? And so let's say you can improve the radius by 10%. Then you can say, well, how much can I improve upon the planet's density or the planet's surface gravity? And then if you know how much you can improve on the stellar radius, for example, then you can do it. And so that's one of the uses that I wanted to bring up. Yeah.
Very nice. That's a great ending point. Romy, I want to thank you very much for walking us through your really lovely article.
Thank you so much for inviting me.
Sure. So you mentioned, you touched upon it there a little bit at the end on like taking Gaia DR3 and going back and reanalyzing past observations. And so let me ask, where do we go in the future to get the most out of this? Are there new observations coming up? Is TESS gonna hit 100 systems? Just sort of where do we go over the next 5 years to continue improving the core mass fraction and other properties of earthy type systems?
Yeah, that's an excellent question. So I'll answer in two ways. So one is hinting at a next project that I'm working on, which is also making use of these equations, and which actually we learned in the process of reanalyzing one of the systems in the paper. And so without revealing too much, we're basically going to use new Gaia parallaxes to try to improve upon.
That was a big hint. Very good, very good.
Yeah, so that's one of the things that I'm working on. And then to try to like elucidate the nature of one of the planets, which we think is maybe a super Mercury. And then going forward, this is useful because one of the things that I'm working on for my thesis right now is looking at trying to constrain the interior properties of small exoplanets. And one way in which we're doing this is by doing exactly that. We're going to be estimating the core mass fraction in terms of the density of the planet and the core mass fraction as inferred from the chemical abundance of the host stars. And for that, we're going to be using test data to try to improve upon existing planets. And so that's one of the future goals that I'm working on right now.
Cool. Let me ask you a question. I don't mean to put you on the spot, but if you got optimal, the best that TESS can do for all of the observables, how well can you get the surface gravity G? Can you get it? You mentioned early in the paper 50%. That's probably okay for some stuff. Can you get it down to 10%? Can you get it down to 1%? How low can you go in G?
Right. That is a great question. And I don't have an exact number off the top of my head, but the uncertainty is dominated in this case by tau. Tau will be the limiting factor, the ingress and egress time.
Okay. Well, that's interesting enough. Okay.
Yeah, because with TESS, basically the observable properties from TESS is going to be the transit depth, and the transit depth can be measured to a very high accuracy and precision. And then the orbital period of force is known almost perfectly precisely with perfect knowledge of the periods, and so the ingress and egress duration is typically the most the hardest to constrain.
Okay, that makes.
But I think we can do, for the best measured systems, we'll be able to do even as good as 10% on the surface gravity, to give you a number. Yeah.
That's great. Awesome. I think there's a bright future going here, and you'll probably have an absolutely wonderful thesis.
Thank you so much.
That'll be great. So Romy, thank you again. And that'll do. And thank you everyone for listening. We'll see you on the next one. Okay, bye-bye.